This week, we initiate the study of optimization problems in the setting of calculus. So problems, we'll see that many problems where we want to find a maximum or minimum of some quantity for some application can be tackled by resorting to the tools and techniques that we've developed throughout the semester. And in order to initiate that discussion, let's begin by looking at what are extreme values. Okay, so let me just give you a brief idea of what we're going to be doing now, what we're going to be concerned about now. So typically in applications, and all the theory of calculus was developed with these applications in mind. So sometimes you have problem of optimizing a shape system, minimize the cost, or try to find how a physical system will evolve in time. And in order to do that, you need to know what is the most efficient way. So, because of some principles in physics that tell you that nature tends to do things in a very efficient way, and so it tends to minimize certain energies and certain actions. And the problem here is that whenever, okay, we can borrow the function notation and we can say, okay, we have a function and we want to minimize that function subject to some restrictions. And now the problem is you can't test forever and compare all pairs of points because there are infinitely many points in R. So what can you do now? Because you want, first of all, to be able to find the minimum value in a finite time. So you don't want for this problem to take you forever to solve it, and also you want to make sure that what you have at hand is a minimum, is your minimizer. Also, you need to, in principle, you would need to compare the value at that point with infinitely many other points. So as you can see, I mean, this is a very, that would be a very naive and pointless way of going about it. What calculus proposes is that instead just using some very localized techniques. So that's why we have the derivative. Derivative is something that is only concerned about what happens near a point, the behavior of the function locally. Then you can reduce this problem with infinitely many points, and you can derive some candidates. And these candidates may or may not correspond to the things you or the objects you're after. So but they're potential minimizers or maximizers. Sometimes they are neither. But effectively, what happens is that this procedure we'll develop now an analysis of finding extreme values reduces the problem in complexity significantly in the sense that instead of testing infinitely many points, you reduce to looking at algebraic equations that usually only involve many points. So now, instead of analyzing all points in R or testing the values for all points in R, which is effectively impossible, you only need to check or sort out 5 points. Among 5 points, which one takes on the maximum value, which one takes on the minimum value, etc. Okay, so this is an effective way of reducing a complex problem to a geometric problem or algebraic problems in this case, because in all the applications here we're going to be dealing with an algebraic reduction. So finding zeros of a function, and that's the principle behind. So we need to be able to recognize these candidates for maxima and minima, and that's what this section is about. So this is section 4.2, extreme values. So the candidates for maxima and minima are going to be the extreme values of a function. So what are extreme values? So extreme values on an interval I. I here is any interval. Okay, maybe the I notation is not good because it's also the same for IM. But okay, so I put it like this. So the interval I may be open, closed, or neither. Open is the case when you have a comma b, all the points that are greater than a and smaller than b, but not a and b included. So this is the open interval. Here you have a closed interval, so it's the same as before, but you're also including a and b, or neither. For instance, this is the case when you have a half open interval, like a comma b, so everything that is greater than or equal to a, but smaller, strictly smaller than b. Okay, so let's start by giving some definitions. So start with a function that's defined in this interval. Remember that I can be closed, open, or neither. Then f of a is said to be absolute minimum if f of a is not greater than any f of x for all values of x inside the interval I. So let's look at a picture, and if this is the interval I, say the interval I is goes from here to here, so this is A, say this is A and this is B. Okay, no, this is bad notation, AB, because then A will not be the point inside. So this is A, say that the interval is interval C, comma D. A here, the value f of A is smaller than any other value of the function in this interval. So f of a is the absolute minimum. F of a is as small as you can get. There may be other points that attain the same value, but you say that f of a, so that's why you refer to the value, not to the point. The a is a point where you attain the minimum, but f of a is the absolute minimum. You look at among all the possible values of f, and the smallest value, if it exists, that's the absolute minimum. Let's look at an absolute max now. It's what you would imagine it is. So it's a point, I mean it's a value f of a that is smaller than or equal to any other value of x inside the interval. So these are very so these are the most important notions. Here's a max and min are what we usually looking for, and so because that leads actually to the definition of to the calling of the process that we're going to be developing for finding these points. So maximum together, maximum, maxima, and minima are known as extreme values. Naturally, I mean, the name is kind of clear, so they're extreme. So the extremes, if you look at the interval of all the values of f, then they are the endpoints, right? So this is as small as we go. F takes values between the minimum and the maximum. So these are extreme values. There's no mystery there behind the notation or the name that we give to these kinds of points. And now, as I said, the process, and this is what is going to concern us for most the remainder of the semester, the process of finding them is called optimization. An important thing, I mean, if not, we wouldn't be introducing these concepts. If, I mean, maybe we would, but I mean, it would be kind of clear that we can always find these values if all functions were continuous and you were always trying to find maximum minimum over closed intervals. Okay, so not every function, this is very important to note, has a max or min. What are the potential problems, you may ask? The interval I, so if the interval I is not closed, for example, f of x is equal to 1 over x, and x is in the interval 0, 1. Okay. So what happens for this function? I mean, what's the problem with this function? So you're here, you have 0, you have 1, and this function here doesn't have a maximum nor a minimum, no matter how big a value is of f at a point, at any point, say this is A, the candidate, you will always be able to find a bigger value closer to 0. So for any suppose this is x, then f of x, you can always find an f of x that beats f of a. And the same thing happens on the other side. If you think you found the smallest possible value, if you get closer to 1, you can always find a value y that's going to be closer to 1. You can always move to the right, and then that allows you to find values that are smaller than f of b for any b in 0, 1. You know, and you see that's why when you close the interval, I mean, this shouldn't be a problem because you cannot move. And once you reach the endpoint, you can never move to the right of the point of the endpoint. So then that problem is precluded in this example. So one problem that you can find, maybe one problem may not allow you to find, or I mean for a max or mean to exist, even if the interval may not be closed. Another problem is that the function may not be continuous. It's not continuous. And as an example, see, f of x is equal to x if x is in the interval 0, 1/2, open, semi-open, and takes on the value 1/4 if x is in between 1/2 included, and 1. Here the interval where f is defined is the interval 0, 1 closed. Okay, so what is the problem in this example? What goes wrong? Okay, the interval is closed, so we're including the point 0 and we're including the point 1. So here this is 1/2. So we move upwards like this as x, and then all of a sudden, when we're about to reach 1/2, there's a hole here in the graph. And what is the value of f of x after 1/2 is 1/4. And now that's the same problem as before. So this doesn't have any maximum value, because you can find points that are arbitrarily close to 1/2, for which f of x is arbitrarily close to 1/2. So for any value of x between 1/2 and 1, the value of f is 1/4. So that cannot be the maximum. But you can always find points that are very close to 1/2, but they're smaller than 1/2. So you pick any number here, say a, some number a. You can always find some x that is closer to 1/2. So this is x, say, such that f of x is greater than f of a. And of course you could, I mean, the function were continuous, then at 1/2 it would take on the value 1/2, and that would be the absolute maximum. So you can take just 1/2, a to be 1/2, and if 1/2 would be the maximum. Like I said, then there wouldn't be anything that would beat 1/2. But it's not the case, because you're putting a hole in the graph. So these are the two problems. The function is not continuous, or the interval is not closed. So the good news is that basically if you avoid these problems, then you'll have a maximum and minimum. So if I is closed, and the function f is continuous, then there is a theorem which guarantees that the function will have a maximum and minimum, will attain its extreme values. So closed interval continuous function, then f attains both a maximum and minimum. Here there are 2 points that I want to make. The first one is the maximum and minimum need not be attained only once. F may attain the maximum and minimum multiple times. It just tells you that there's one at least, so it attains the maximum and minimum value at least once. The other thing is that you just need continuity. The function doesn't need to be differentiable, and one of the examples that we always use for this is the absolute value, which is not differentiable. Yeah, we know that. Okay, so we have the interval -1, 1, so the function here is looks something like this. So this is f of x equals the absolute value of x. Naturally, this function here is not differentiable at 0. I mean, we've discussed that many times, multiple times now. This is not differentiable at 0, but it's continuous everywhere. And you see that the 0 here is the f of 0 equals 0 is a minimum. And what is the maximum? F of 1. So f of 1, which is the same as f of minus 1, which is 1, is the maximum value. So these are the extreme values. So it attains the minimum, the absolute minimum once, and the absolute maximum twice. So now we'll discuss how to find these maximum and minimum values for functions in general. I mean, we'll develop a sort of heuristic argument, and from there we'll turn that into a procedure that we can apply to most problems. I mean, trust me when I tell you that this is going to be very easy once we implement it, and we'll see a few problems. It's going to be kind of hopefully clear. So that we'll talk about that in the next video.